Hi, everyone. I am extremely honored to be invited to participate in this conference. I'm Yu Baojian. The topic I'm about to share is will the current method achieve reliable design for structures? The outline of my report contains the following two parts. The first, applicant resume. I received my PhD in 2007 at the College of Civil Engineering in the Southeast University, and I visited the University of Liverpool in 2015. Now I am the chair of structural engineering in the School of Civil Engineering of Changsha University of Science and Technology. I was the chair of MS 36 anti-collapse performance evaluation and the reliability improvement of engineering structures in EMI 2023 and the MS 14 uncertainty quantification and the reliability-based performance evaluation in EMI 2018. I was the member of American Society of Civil Engineers and the Seismic Committee of China Association for Engineering Construction Standardization. In 2010, I received the Science and Technology Progress Award first prize from the People's Government of Hunan Province. And in 2016, I received Youth Elite Award in Hunan Province. I was the Honorary Research Fellow in Institute for Risk and Uncertainty of Liverpool University and was supported by Hunan Provincial Natural Science Fund for Distinguished Young Scholars in 2022. My research stands on three fundamental footings: numerical fitting, structural reliability methods, and design and construction optimization. The specific research areas include structural uncertainty quantification across length scales, naval structures of high anti-progressive or seismic performance, green or intelligent construction technologies. I received the research fellowship by National Science Funding of China and was a member of the winning project team in the National Basic Research Program of China on basic theory research of safety design and evaluation of super long span bridges. I have obtained about 3.36 million yuan of competitive research funding at a principal investigate, published 4 books, 59 documents, and so on. Next, we will present some of the team's research results, the design methods for beam string structure based on reliability. We know that the non-uniform snow and ice disaster load occasionally cause the collapse of long-span spatial structure. Therefore, we take the long-span beam string structure as an example and explore the reliability of bearing capacity and the anti-progressive collapse performance. We established the finite element model of two BSS models, BSP and TSS, and discussed the ultimate bearing capacity of the models and the different load ratios. As shown in the table, with the increases of load ratio from 0.1 to 20, the ultimate capacities decrease dramatically. Then we discussed the variation coefficient of the ultimate bearing capacity of BSS and the random load ratio and the fixed load ratio. We know that the random load ratio has an important effect on the variations of ultimate bearing capacity of BSS. In order to obtain the variation law of bearing capacity and the different load ratios for BSS and the combined full span and half span loads, a practical bearing capacity model is proposed. Through fitting the data of bearing capacity of the 8 models, it shows that the fitting residue are small and the proposed model is good. Using the bearing capacity model mentioned earlier, the failure equation of BSS and a random load ratio was established. From the table, we can see that the reliability indexes obtained by the two different methods are close to each other. Through reliability analysis with different conditions, we can conclude that the reliability index with RLR is lower than that with FLR, and they both decrease with the increase of load ratio. The reliability index varies greatly under different cases. Based on the previous discussion, we proposed two improved methods. Improved method 1 adopts 3 sets of fixed design factors. Improved method 2 adopts the constant gamma G, gamma Q, which are the average values of the improved method 1, and a variable gamma R, which is shown in the figure. Now let's discuss the effects of different design methods on the coefficient of variation of reliability index. Obviously, the coefficient of variation with improved method 2 is generally smaller than those with improved method 1 and the current method. We also investigate the influences of the improved method on collapse of BSP and obtain the corresponding results. It shows that the performance of anti-progressive collapse of the BSS designed by the improved method 2 is slightly improved compared that by the improved method 1. However, it collapsed under design load and its performance is poor. Based on what has been discussed above, we can draw the conclusions as follows. With the increases of load ratio of half-span load to full-span load, the ultimate capacity of BSS decreases dramatically. The randomness of load ratio has a significant influence on the variations of the ultimate capacity for BSS. The improved method 2 can effectively improve the reliability robustness of BSS bearing capacity and the random load ratio, but has little effect on improving the anti-progressive collapse performance of BSS. How to develop an effective method to achieve reliable design for structures needs further research, especially on anti-progressive collapse performance. That's all.